Welcome back yet again to another episode of Dave Does Math from Home. Today we're talking about section 3.9. We're skipping a couple stuff in the middle. 3.6 we're just not doing at all. 3.8 we'll pick up after the next exam. 3.8 is where stuff starts to get really weird and fun. And I want to sort of tie this stuff up with an exam before we get into that. So we'll come back to 3.8. 3.9 is pretty quick. It's relatively straightforward. You may have been wondering throughout the last several sections, we have taken derivatives of polynomials, rational functions, exponential functions, trig functions. We've done all of them, and combinations of them, like weird compositions of exponentials inside of trig functions. We've done all kinds of crazy nonsense. What we haven't done yet, what we've really been missing, what we've been hoping to see this whole time, is the logarithms. So today we're going to talk about how to get the derivative of the logarithm. And for this I'm basically just going to present sort of like a graphical approach here. If we want the derivative of the natural log, I'm going to suggest that we start with a basic idea of what a natural log looks like. Natural logs kind of have this shape. They are really, really steep back here. This is a vertical asymptote, so they get kind of infinitely steep. If we're considering the slopes at various points. Down here it's really steep. If you go further down it gets kind of infinitely steep. Here it's still steep but less so. This is moderately steep. This is starting to taper off. It's still positive, it's just a much less exciting positive. Over here, it's not zero, it's a small positive, and a smaller positive, and an even smaller positive. It never quite gets to zero, but it gets close to zero. It gets really flat the further out you go. Like, it's still always positive and always increasing. It's just increasing at a minuscule, almost insignificant amount. So it gets to zero-ish. So, if I want to draw a graph of the derivative, I need something that close to the axis is going to be almost infinitely large, but decreases pretty swiftly through here, starts to flatten out, starts to get close to zero, gets really, really close to zero over here. This is the graph, if you are looking at shapes and trying to identify what function this might be. This is the graph of a rational function. It has a vertical asymptote here. The closer you get to zero, the closer this gets to infinity. It doesn't exist at zero. It has a vertical asymptote here, and it has a horizontal asymptote as x moves out to infinity. It gets really, really close to zero. This is a graph of perhaps the most fundamental and basic rational function there is, 1 over x. This gives you the horizontal asymptote at 0 when x gets really, really big. Horizontal asymptote at y equals 0 when x gets really big. Gives you the vertical asymptote at x equals 0 as y gets really, really, really big. So it is in some ways sort of surprising that when you take the derivative of a natural log, you get a rational function. But it is what it is. The graphs line up, it makes a certain amount of sense. It's a little bit weirder than the exponential graphs. Like, when we did, the exponential graphs are really cool, because when you take the derivative of an exponential graph, you get an exponential graph. If you take a derivative of e to the x, you get e to the x. Its derivative lands perfectly on itself. That's kind of neat. It sort of like stays within the family. This derivative jumps to a different family. It's going to be an e to the x. Now that we know this, we can do weird stuff with chain and product rules. And quotient rules as well. I just don't mention them as much because they're just, like, computationally, it's just like the product rule plus a bunch of other steps. Oh, I'm about to run out of battery. I better make this quick. Consider a function like the natural log of x cubed minus e to the x. If you wanted a derivative, you'd have to get the inside, which is x cubed minus e to the x, and take a derivative of that, which is 3x squared minus e to the x. You'd have to look at the outside, which is natural log of a blob. Derivative of that is 1 over the blob. And you would find f prime of x by using the chain rule to combine these things. You would get 1 over this stuff times the derivative. Lots of textbooks are going to write it with this on top of this. We'll sort of simplify this. That seems unnecessary. It seems like a simplification that I don't want to do. You'll also, in other problems, you'll see the natural log on the inside of some chain rule stuff. That also works exactly like you'd expect. I'm going to skip an example of that one because I don't want to spoil too much of the homework. Homework should be an exciting journey of discovery for you. And also, my camera's about to die, so I have to wrap this up right now. Good luck with the homework. Email me questions.